I want to finish up section 2.3. In this section, we introduce the idea of how to solve a linear first order differential equation. And we want to write the DE in what we call its linear form, and then from that, determine its integrating factor and then solve. So the method that we gave before is basically what we try to walk through each time that we're solving. So here, the method for solving linear equations, we want to force the equation to be exact by determining, here initially we call it a linear factor, but that linear factor is indeed the so-called integrating factor. Once I know it, multiply the entire equation by the integrating factor. Before you do that, you want to make sure that the equation is written in this form here, number 2, that second equation. The equation must be written in that form, and then you can extract from that the integrating factor. Remember, yesterday we took a long time trying to just produce, why we call the integrating factor the so-called integrating factor. So now that we know that, it is well defined. The integrating factor is e to the integral of that px dx. Multiply that through the equation number 2. And then once you have that, again, the equation is written in that standard form of 2. We're going to determine the integrating factor, that e to that integral, multiply everywhere, both sides by the integrating factor. The left side is already the result of the derivative of the product of the integrating factor and the dependent variable, which typically is y. The independent variable is x. So the left side is already the derivative of the product of these two is equal to the integrating factor that you multiply to both sides times that f of x. And so what you have left is integrate both sides. The integral of the left side is the integral of the derivative. So by the fundamental theorem of calculus part 2, that result is just this identity with what we have there in the bracket. So no work there. So the work that you're doing is simply on the right side by integrating this integrating factor times that f of x. So we looked at number 4, very simple one. Let's look at the next one. So here, need a pen. This is x times y prime plus 2y equal to 3, if I can write it like that. X times y prime plus 2y is equal to 3 is not in the form that we want, you recall, has to look like y prime plus p of x times y is equal to some function of x. Now, 2 or 3 things there are important that you need to note. One, what they're saying is that derivative has to be by itself. So that dy over dx has to be written by itself. So if there's something multiplied to it or divided by it, you got to get rid of that. So that's the first thing. So here, for our problem, x is multiplied by the y prime. So we got to do something with that x. The second thing that this equation is saying, equation number 2, that is that y prime plus p of x times y is equal to f of x. One, nothing can be associated with this derivative. Secondly, there has to be a y by itself here, this p of x times y. It cannot be y to the second power or y to the third or y to the negative first power. Yes? If that happens, we call that a special case of the linear function. We call that a Bernoulli equation. It could be Bernoulli or it could be Ricotta or some other form. But here for the basic linear equation, you want this y to be to the first power. Then thirdly, first thing is whatever is associated to y prime has to be 1, the coefficient there. Secondly, this has to be a y to the first power here. And then whatever else is associated with it, translation, its coefficient has to be a function of x alone. That's what that means. So I can't have any more y's there. Right? And then 1, 2, 3. The fourth thing, the fourth thing is that this f of x has to only be a function of x alone. So again, no x's and y's over there. If that's the case, then we have a special case that we call perhaps Bernoulli or some other form that we can solve. But we have to know how to first solve this guy first. So let's look at this problem. We're going to divide through by an x so that that would leave the coefficient of y prime as 1. So here we have y prime plus 2 over x times y is equal to 3 over x. So this is in standard form. So our integrating factor is mu equal to e to the integral of 2 over x dx. So this is e to the 2 times the natural log of x. So this is e to the natural log of x squared, and that's just x squared. So I'm going to multiply this equation here, everything by the x squared. So this is x squared times y prime plus x squared times this 2 over x times y is equal to, sorry about that, that's x squared. Why am I writing 2x? Multiplying by x squared, then we multiply by x squared over here times 3 over x. And so, again, simplify, this is x squared y prime plus 2x times y is equal to 3x. Yes, sir. The left side is automatically the derivative with respect to x of the product of the integrating factor, which is x squared, right? The integrating factor, mu equal to x squared, integrating factor, and its dependent variable, which is y, is equal to 3x. Again, you see that this is the derivative of x squared times y. The derivative of the first is 2x times the second plus the derivative of the second, which is y prime times the first, x squared. So I integrate both sides. So the integral of the derivative, according to the fundamental theorem of calculus part 2, is just this function, which is here just x squared times y, and that's equal to 3x squared all over 2 plus some constant. Divide through by the x squared to get the y by itself, if that's possible. Sometimes it's not easier to do that. So just say this here implies that y is equal to 3 over 2 plus c divided by x squared. Now we look at the solution, and just a comment on this idea of the transient form. The transient form simply means that if I take the solution, if I find its limit, which part of that limit goes to 0. And so whichever part of that solution, or sometimes even the whole solution, may go to 0, then we say that the part that does go to 0 as x goes to infinity, we call that the so-called transient form, or the transient term for the solution. So So here, note if as x goes to infinity, c divided by alpha x, and it could be c times alpha x, doesn't matter, but c divided by alpha of x goes to 0, then we say that c all over alpha of x is transient. What they're looking at and examining is in certain functions, well, any function or polynomial, or whether it's polynomial or not, there is said to be a term that acts like the head, and then the rest of it acts like the tail. And so we call that basically some type of asymptote, where a function tries to approach its asymptotic value. What it tries to approach is said to be the head or the biggest term. In my field of computer programming years ago, in what's called the study of algorithms, they call that the biggest O. And typically that big term in terms of computer crunching numbers is said to be, if the computer fails or crashes, it's going to crash trying to approach its leading term or its biggest O. And so anytime there's a malfunction, we try to fix that part. Typically the head is, if you go after the head, fix that, then the tail is trying to approach the head, but the tail never becomes that. So we look at the biggest term. So here, what happens to the limit for a particular solution? And if that limit goes out to 0, then and later on in this, the second part of this course, we don't offer it here. There is examination about this transient term. We call it approximation theory. So there is something, and I'm trying to recall, and it may be here in this class where, and I'm sure when we get to that, I think about this statement here, that most of our answers would be confined to wherever that constant term is, that the true nature of the answer of that particular differential equation is consumed by that constant times something else. So you want to be very careful. Let me say this. You want to be very careful then that you don't forget the constant. Because just throwing that out or just saying, oh, we don't need that, a lot of times when you have initial condition, you plug those initial conditions in, these parts over here, like cx squared over 2, that probably will go out or be some very small number. But the big chunk of the answer will be consumed with this c divided by x squared. So we don't take c lightly. Well, let's look at another one. Okay, I'll do this one, and then I'll give you one to do for a couple of minutes, maybe number. Let's see, which one? You want me to do 3 and then you do 5, or I do 5 and you do 3? I do 3. Okay. Is everybody in agreement with that? Okay. Okay. I would always think, let the teacher do the problem that's like the big number problem, like whatever. And then the class, we'll do like number 1, 2, or 3, right? And but anyway, I do 3. So this is y prime plus y is equal to e to the 3x. So here, p of x is whatever is multiplied to y. That's just 1. So here our integrating factor, mu, is e to the integral of just dx, which that's just e to the x. So I multiply everywhere by e to the x. So this is e to the x times y prime plus e to the x times y is equal to e to the 4x, right? E to the x times e to the 3x is e to the 4x. The left side is automatically the product of the derivative of the integrating factor, the product of the derivative of the integrating factor, which is e to the x, and the dependent variable, which is y. That's equal to that right side, e to the 4x. Integrate both sides. So the integral of this derivative of e to the x times y dx is equal to the integral of e to the 4x dx. Integrate the left side, it's just the e to the x times y, and that's equal to 1/4 times e to the 4x plus the constant. Now we can divide everything through by that e to the x and just leave the y equal to. So how did I get 1/4 there when I integrated e to the 4x? U du. Yes, sir. Bless you, my brother. U du. Yes. So here, y is equal to 1/4 times e to the 4x divided by e to the x. So it's just e to the 3x plus c all over e to the x. And you can see that the transient part is this c over e to the x. It acts, that's, I think, also for the interval. So here, in terms of the transient form, its interval is based on where the x values are said to be continuous. So here, c over e to the x, x can be any real number, and so we're fine with that. In other words, if x is 0, e to the 0 is 1, so I'm dividing by c divided by 1 and not c divided by 0. So 0 is allowed. Trying to find the previous problem. So for this number, c over x squared is transient. What's wrong with this computer? Here on the interval from 0 to positive infinity doesn't include 0 because c divided by 0 would give us something that's not defined. So that was number 3. Okay. All right, you do number 5. Let's give you a couple of minutes on that. So here, it's in the form, so your integrating factor would be e to the integral of 3x squared dx. So that gives us e to the 3x squared plus 1, so 3x to the third divided by 3. So we just get e to the x to the third. Oh yeah, this was the one that I was looking for. Yeah, this is the good one. Yeah. I thought it was number 7, but it's this one. So we plug everything back in, multiply the equation by e to the x cubed. So we get e to the x cubed times y prime plus 3x squared times e to the x cubed times y is equal to x squared times e to the x cubed. So the left side is the derivative of the product of e to the x cubed times y, and then we have to work to integrate on that right side. All right, so we integrate both sides. Equal to the integral of x squared times e to the x cubed dx. That right side was a problem in calculus 2, and it involved a trick. And if you remember that trick with the e to the u du, and then from there use a u du substitution, you can get it. So let u equal to this x cubed. The du is 3x squared dx. And so the x squared dx is the 1/3 du. So this implies that 1/3 du is the x squared du. So the left side over here is just e to the x cubed here times y. That's equal to 1/3 times the integral. Now that du picks up times the 1/3 picks up the x squared dx for us. And so all I have here is e to the u du. And then I integrate e to the u du. Well, the integration of e to the u du is just e to the u plus some constant. So this is e to the x cubed times y is equal to 1/3 times e to the u. I can go ahead and just put that u back in there and write the answer, e to the x cubed plus some constant. Divide both sides by e to the x cubed, and so y is equal to 1/3. Notice if you had thrown away this constant c, you would think your answer is just y equal to 1/3, which is not the case. It's more than that. Plus, here's the big part of it, c divided by e to the x cubed. And again, this is your transient part, and it exists on all real numbers. Okay. Okay. Any questions there? All right. Let's see if there's... So you got those problems. There's problems here. I want to work one of those with the sine function in there. So where am I? I'm there. These should be very straightforward. Just want to work through 7, and if I go quickly, Again, those steps is what we're using, and so they're just very straightforward. I want to write this in the form, so divide everything by the x squared. So this is y prime plus 1 over x times y is equal to 1 over x squared. The integrating factor is just x. Mu is equal to e to the integral of that 1 over x dx. Well, this is e to the natural log of x, so it's just x. Right? So the left side automatically is the derivative of the product of the integrating factor x times the dependent variable y is equal to the integrating factor x times 1 over x squared, which is just 1 over x. So I integrate both sides, so I have x times y is equal to the natural log of the absolute value of x plus some constant. And so y is equal to 1 over x times the natural log of the absolute value of x plus c divided by x. The transient part is c over x, and it exists on the interval, open interval from 0 to positive infinity. Is everybody happy with that? Okay. Let's look here and see. Okay, this guy right here. This is a good one. Number 9. Divide everything through by x. So this is, so I have y prime minus 1 over x times y is equal to x times sine x. See how I divided everything by the x, including that x squared sine x? So divided that by an x, had left x sine x. So the integrating factor is e to the negative integral, that's negative 1 over x dx. So this is just 1 over x. Right? This is 1 over x, right? If it's just e to the integral of 1 over x dx, you know that just becomes out e to the natural log of x, which is just x, but it's a negative in front of it, so it's x to the negative 1 over x, right? So you multiply everything through by the 1 over x, so the left side is the derivative of the integral of the product of the integrating factor, 1 over x, times the dependent variable y. That's equal to, here, the integrating factor multiplied through everywhere, so this is the right side is just sine x. X times sine x times 1 over x is just sine x. Integrate both sides. The left side is just 1 over x times y is equal to the integral of the sine x, that's negative cosine x plus some constant. Multiply everything through by the x, and so y is equal to negative x cosine x plus x times c. Right? And this is not transient. So c x times c does not go out. As x goes to infinity, x times c also blows up into infinity. Okay? Yes, sir. Did you come late? You didn't? Huh? Thought I wrote it down. It's on the next page. I think I put it there. It's down here. If as x goes to infinity, c over some term goes to 0, then we say that c over that term is transient. Okay. That's all they're talking about. And I tried to give the synopsis of looking at the application of computer programming of the big O when I was talking about that. I was talking about this so-called transient form. Yes, sir. Okay, so let's see. Number 13, reckon I can maybe work that. There should be enough for you for this. Oh, 21 is the one that I always leave with, but which one should I do, 13 or 21? 21? Okay. We'll do 21, then I'll move to section 2.5, okay? So here the independent variable is theta, the dependent variable is r, right? R depends on theta. Based on how it's written, dr divided by d theta, right? So typically it's dy over dx, so y is the dependent variable, x is the independent variable. So here it's dr over d theta, so r is dependent upon theta. So it's in the form that you want, and so here we have our integrating factor. Here we say that mu is equal to e to the integral of the secant, this is secant theta times r. If we're thinking about dy over dx plus some p of x times y equal to f of x, but for this problem it's dr over d theta plus some p of theta times r is equal to some f of theta. Right? So here our p of theta is this secant theta. So this is e to the integral of secant theta d theta. And so mu is that integral of secant theta d theta is the natural log of the absolute value of secant theta plus tangent theta. So this is e times the natural log of the absolute value of secant theta plus tangent theta, and that just gives us the natural log of the absolute value of secant theta plus tan theta. So the left side becomes the derivative here with respect to theta of the product of the integrating factor and the dependent variable. Here the dependent variable is r, so I'm going to write that first, r times the natural log of the absolute value of secant theta plus tangent theta. Excuse me, that natural log goes out, forgive me. E to the natural log just becomes that secant theta plus tangent theta. I'll be dang gone. Okay. Nazra, that was your turn to say something. Okay. Secant theta plus tangent theta. So this is r times parentheses that secant theta plus tangent theta d theta. And that's equal to, we've multiplied both sides by the integrating factor. So this is the cosine theta, which is here, times this secant theta plus the tangent theta. Simplify that that right side, because secant is 1 over cosine and tangent is sine divided by cosine. So what I have is the derivative with respect to theta of r times secant theta plus tangent theta d theta is equal to 1 plus sine theta. Uh-oh. Again, cosine times secant. Well, secant is 1 over cosine. So cosine times secant is just 1, right? And tangent is sine divided by cosine. So cosine times sine divided by cosine is just sine. Right? So now we do. Great. Thought I'd make a little math funny. No. It doesn't work. Save the jokes for the comedian. Take that d theta off of these two parts here. I was not integrating down here, so it didn't need the d theta there. So it's equal to the integral of 1 plus sine theta. Is r times secant theta plus tan theta. We integrate that right side with respect to theta, so the integral of 1 d theta is just theta, and then the integral of that sine is negative cosine theta plus c. I'll just leave it just the way it is. Too much going on, right? So when too much is going on, we just leave it as is, and we're done. Any questions there? All right.
You have to determine if it's transient, if it's a grade function.
It's possible. I don't know if they asked for this problem or not, but hopefully they don't, right? Yeah. On the test, I do not ask for that. That's just only something in web assign. Okay. All I'm concerned with is that you give me the answer. Right. Close out here and open the next section.